So this is a ski lift. So it's fabricated from standard circular hollow section, and it's got an outside diameter of 60.3 and a wall thickness of 4 millimeters. Calculate the stresses in the tube at this location XX when it's supporting 2 people, and they both weigh 100 kilograms. So we have our formula that we'll be working with. So we have our 2 people. We always work in applied force, where force is our mass times by our acceleration or gravity. So our 200 kilograms is the equivalent of 1,962 newtons. If that's the XX, we've got at this point here 1,962 newtons going up. And there's also through the neutral axis of the tube, we have 1962. So that's representing the weight of the 2 people. You have this distance here. That's our E, our eccentricity. That's the 300. So there'll be this moment M. So we've worked out what the force is. Let's look at the area. So we've got 60.3 outside diameter, and then we've got a 52.3 internal diameter because it's a 4 millimeter wall thickness. So we've got our force. We can work out our area in terms of our moment. Our XX, it's our force times by the eccentricity. The problem is how do we get our Z value? You'd have to look at tables for that. From the table, our Z is 9340 millimeter cubed. You haven't got a table for this, but if you had to do an example for a hollow tube, then you'd be given a table. The area from the same table, or if you work it out, should be 7.07 centimeters or 707. If you've got these chaps sat on this, we've got the whole thing is in tension. So what we'll say is tension is positive. Okay, in the last example we said that compression was positive, so we're going to say that tension, so in terms of our direct stress, is going to be plus F over A. Then which side is going to be in tension and which is going to be in compression? Now as these are applying the load sort of downwards, it's going to rotate around this way. That's going to move across to here. So this side is going to be in compression, and that side is going to be in tension. So we're going to end up with compression on this side and tension on that side. In terms of right now our formula, our stress, so our stress on this side is plus 66 or 65.8. and our stress on this side is minus 60 newtons per millimetre squared. So in terms of designing your material, you do need it to cater for tension, which is what you would expect, but because of the way that it's designed, you also need it to cater for 66 newtons per millimetre squared. The difficult part of that was, it's just trying to work out, if you've got a force there, which side is the tension or the compression as it's twisting across. So again, as these people are applying the load, there'll be a twist that way that will create a compression on this side. So therefore that's why we're taking away 63 on the right hand side, and it'll have a tension on this side. That's why we're adding our 63.